Hello everyone, I am Sudheep from 3rd Year ECE. In this video, we are going to discuss about different methods used by CPUs of digital signal processors to perform arithmetic operations. In order to process real-world data, we need to select a digital signal processor and DSP algorithm suitable for the required application. We can choose any one of the floating point method or fixed point method to perform arithmetic. Fixed point DSP uses 2's complement integer to represent and manipulate the data, whereas a floating point processor uses a mantissa and exponent in addition to the integer format to represent a number and perform operations in the data. Let us first discuss fixed point format. First, let's understand 2's complement representation of a number. Step 1 of conversion of decimal number to its 2's complement form is magnitude of the decimal number is converted to its binary number. And then second step is if the number is positive, then its binary number itself is its 2's complement representation. If the number is negative, then perform 2's complement operation, that is negate the digits of the binary number, which is called 1's complement, and then add logic 1 to the data. Let us try to understand with an example. Consider 3-bit 2's complement representation given below. For 3-bit, we can have dynamic range from -4 to 3. For all positive numbers, corresponding binary number itself is its 2's complement as mentioned previously. For negative numbers, for example here consider -3, binary number of 3 is 0, 1, 1 and its 1's complement is 1, 0, 0. After adding 1, 2's complement is given as 1, 0, 1. Now let us perform a multiplication operation. Say 2 into -1, that is 0, 1, 0 into 0, 0, 1. Here for 2, we considered its binary form 0, 1, 0, which is also its 2's complement form. For -1, take binary representation of 1. We get the result as 0, 0, 0, 1, 0. But as 2 into -1 yields a negative number, then 2's complement of the result is 1, 1, 1, 1, 0. After removing the two extended sign bits, we get the answer as 110, which is -2 as evident from the previous table. But there is a problem. Sometimes results of arithmetic operations can cause overflow problems. Here consider 2 into -3. That is, we can write as 010 into 011, where 011 is the binary equivalent of 3 and the product is 00110. And the 2's complement of the result is 11010, and after removing two extended sign bits we get 010, which is equal to 2. But the correct answer is 2 into -3 is equal to -6. What causes the problem is -6 is not in the range of -4 to 3. So this is called overflow problem. To overcome this overflow problem, we can go with 3-bit 2's complement system using fractional representation. In this system, we normalize our range between -1 to 1. Here we can observe -3 is represented as 3 by 4, 2 as 2 by 4, -1 as -1 by 4, and so on. And so 3 is represented as 0.11, whereas in its 2's complement form it is 011. Similarly, -1 here is 1.11 and 111 in its 2's complement form. Let us see how overflow problem is resolved here. Consider same 2 into -3 example as previously. We can write it as 0.10 into 0.11 and the product is 0.0110, whose 2's complement yields 1.1010. Let us convert this 1.1010 into decimal form to verify whether the answer is correct or not. We can write 1.1010 as -1 into 0.0110. If we calculate this, we get it as -3 by 8. From the table, 2 into -3 is equals to 2 by 4 into -3 by 4, which is equals to -3 by 8 and same as the previous result. Hence, overflow is avoided. Next type of representation in fixed point format is Q format representation. Under this, let us understand Q15 format here. This represents Q15 format where data is in sign magnitude form, in which there are 15 bits to represent magnitude and 1 bit to represent sign. After sign bit, we have a point representing binary point. A number is normalized to range of -1 to 1 which is divided by 2 power 16 intervals, each of size 2 power minus 15 in this format. And we can observe most negative number is minus 1, while most positive number is 1 minus 2 power minus 15. Let us take an example to understand how to convert a number to its Q15 format. Consider 0.560123. First multiply 0.560123 with 2. We get 1.120246. From this, take out this 1 and multiply the remaining 0.120246 with 2. We get 0.240492. Take out the 0 and again multiply 0.240492 with 2 and continue this process up to 15 steps. Finally, we get the Q15 format represented as 0.100011110110010. To verify our result, perform 0.560123 into 2 power 15. We get 18354 in decimal. If we convert 18354 to its binary form, we get the same result as above, that is 0.1000111110010. Similarly, let's consider Q15 representation for a negative number. Consider minus 0.160123. First, let us consider its magnitude 0.160123 can be represented in Q15 format as 0.0010100111110. Then after applying 2's complement, the Q15 format becomes 1.1101111000010. We can perform this in an alternative way. Minus 0.1600123 into 2 power 15 gives minus 5246.9. We can truncate this to minus 5246 and find its 16-bit 2's complement, which is given as 1.110101110000010, which is same as the previous result. Now let us discuss the second format, that is floating point format. Using floating point format, we can increase the dynamic range of number representation as compared to the fixed point format. Its representation is given as x equals to m into 2 power e, where m is mantissa or fractional part in Q format and e is the exponent. Always m and e are the signed numbers. Here in this floating point representation, we have 4 bits for the exponent and 12 bits for the mantissa. And mantissa has a range from minus 1 to 1. Dynamic range is controlled by the number of bits assigned to the exponent. Higher the number of bits assigned to the exponent, the higher the dynamic range. The number of bits in the mantissa defines the interval in normalized range. Interval size is 2 power minus 11. Here we can see the most negative number as minus 128, most positive number is given as 127.9375 and the smallest positive number is given by 2 power minus 19. Let us take an example to convert 0.160123 to the floating point number. Let us try to write this number in m into 2 power e format. We can observe 0.160123 by 2 power minus 2 gives 0.640492. So we can write 0.1600123 equals to 0.640492 into 2 power minus 2. Remember that the range of m is from minus 1 to 1. Using 2's complement, minus 2 can be written as 1110. Using Q11 format, 0.640492 can be written as 01010001111. Cascading the exponent and mantissa bits gives 1110, 010, 1000, 11111, which is its floating point representation. Here we can take any value in between minus 1 to 1 in place of 0.640492 and vary the exponent value accordingly. Let us see how to decide which processor to use for which application. Fixed point method represents only a very narrower dynamic range of the integer number. We need to spend much more coding effort to design fixed point DSPs. Floating point DSP offers a wider dynamic range of data so that coding becomes much easier. However, the floating point DSP contains more hardware units to handle the integer arithmetic and the floating point arithmetic. Hence, it is more expensive and slower than the fixed point process in terms of instruction cycles. Making the DSP and ASIC a chip designed for a particular application, a dedicated hand-coded fixed point implementation can be the best choice in terms of performance and small silica area. Coming to fixed point DSPs, companies like Analog Devices, Texas Instruments, and Motorola manufacture fixed point DSPs. Analog Devices offers a fixed point DSP family such as ADS P21 family. Texas Instruments also provides various generations of fixed point DSPs. Some of the most common ones are TMS320C1 family, TMS320C2, TMS320C5, and TMS320C62. Motorola also manufactures a variety of fixed point processors such as DSP5600 family. Coming to floating point DSPs, Analog Devices provides the floating point DSP families such as ADS P210 family and Tiger Shark. Texas Instruments also offers a wide range of floating point DSP families, in which the TMS320C3 is the first generation, followed by the TMS C3 320C4 and the TMS 320C67. Thank you.